Hello everyone. In this next set of videos, we're going to tackle the fundamental problem of representing a vector in terms of elements of a given set of vectors from a vector space. But before we begin, let's take a few moments to recall the definition of a vector space. So recall that a vector space is a set of elements which or is endowed with two operations, O plus and O times. And these operations and V should satisfy the 10 conditions as shown. So henceforth, when V is a vector space with operations O plus and O times, we will simply denote the vector sum of U and V by U plus V instead of U O plus V. Similarly, to denote the scalar multiple of U by C, we will just write this Cu instead of Co times C. Okay? So what do we mean by representing a vector in terms of elements from a given set of vectors in a vector space? Here is the precise description of that statement. Suppose we have a set of vectors, say V1, V sub 2 up to V sub k, a vector V in the vector space is said to be a linear combination of the vectors coming from the set if there exist scalars r sub 1, r sub 2, up to r sub k, such that V can be expressed in this manner, meaning V is a sum of scalar multiples of V, the V sub j's with uh, scalars given by the r sub j's. Okay, to illustrate the idea, suppose in R3 we have the vectors v1, v2, and v3 as shown. Observe that if we multiply v1 by -1, v2 by 2, and v3 by 3, and add the resulting vectors, then we would get the vector -6, -3, -1. In other words, this vector is a linear combination of the vectors v1, v2, and v3 via these scalars. Note that in a vector space, every vector is a linear combination of itself, because a vector can always be viewed as a scalar multiple of itself by the scalar 1. Moreover, the zero vector is always a linear combination of any set of vectors. It's because we can write the zero vector as linear combination with scalars all equal to 0. In R2, consider the vectors 1, 1, and 2, 2. Observe that the zero vector can be expressed as 0 times the first vector plus 0 times the second. And you can also write the zero vector as the scalar multiple of the first vector by 2 plus the scalar multiple of the cyclic vector by -1. So this shows that the zero vector can be expressed as a linear combination of 1, 1 and 2, 2 in at least 3 ways. In fact, in general, there may be several ways of expressing a vector as a linear combination of a set of vectors. That's the same as saying that when you obtain a linear combination for V in terms of V1, V2 up to V sub k, then your scalars need not be unique. So how do we determine if a vector is a linear combination? It turns out that this problem is just a problem of solving a system of linear equations. We describe the process. Suppose we want to determine whether or not a vector V is a linear combination of a given set of vectors, V1 up to V sub k. What we do is we set up the equation that we want to solve. So we want to find scalars, R1, R2 up to Rk, that will make this equation true by definition of linear combination. In this equation, the R's are variables to be solved. They are unknowns at this point. And this actually is or can be viewed as a system of linear equations which can be solved by Gauss-Jordan, for instance. Now, if this equation has a solution, then we can conclude that V is a linear combination of V1 up to V sub k. Let's illustrate this idea. In R3, consider the vectors 4, 2, -3, 2, 1, -2, and -2, -1, 0. Let's determine whether or not 4, 2, -6 is a linear combination of the given vectors. As described earlier, the first step is to set up the equation that must be satisfied. Okay? So we need to find scalars R1, R2, R3 such that with these scalars, 4, 2, -6 is a scalar or is a linear combination of the given three vectors. Now observe that the left-hand side is or can be expressed as a 3x1 matrix. Why? We perform scalar multiplications here. So that will produce a sum of 3 vectors in R3. Okay. If you add them up, then the result will still be a 3x1 vector. So this vector here. This is a 3x1 vector resulting from this expression. But this 3x1 vector can be written as a matrix product by the definition of matrix multiplication. It is equal to the product of this 3x3 matrix by this 3x1 matrix. Observe that this 3x1 matrix contains as entries the variables or the scalars that we are looking for, R1, R2, R2. And here In this 3 by 3 matrix, you can observe that the columns are exactly the given vectors above. Okay, so going back to our problem, we are solving for R1, R2, R3. So we want to solve this linear system. So we just need to consider the augmented matrix as shown. So applying Gauss-Jordan process. Okay, so this is the augmented matrix. So if you apply these 4 elementary row operations, you can verify that the augmented matrix is row equivalent to this augmented matrix. And recall that this system and this system has the same solution set. So this augmented matrix tells us that the system has infinitely many solutions given by R1 equals 2p minus 2, R2 equals 6 minus 3p, and R3 equals. That's the solution set because we see from the augmented matrix, the last augmented matrix, that column 3 does not contain any leading one. Okay, so the variable associated with this column, with the third column, is a free variable. That free variable is assigned to be p. Okay. So to give an example of a solution, we can just give an arbitrary value to t. So one, well, a best choice would be t equals 0. So if you plug in 0 here, you'll find R1 equals negative 2, R2 equals 6, R3 equals 0. And indeed, you can verify that with these values, 4 to negative 6 is a linear combination of the given 3 vectors. In fact, our solution shows that we can write 4 to negative 6 as a linear combination of these 3 vectors in infinitely many ways given by the solution set of the linear system that we solved. Here's another example. Now consider the same set of vectors in R3 in the last example. This time, let's determine if negative 1, 2, 3 is a linear combination of those vectors. So following the same set of steps in the last example, we set up the equation to be solved. We're looking for scalars R1, R2, R3, making this equation true. And you can turn this into a matrix equation, okay, which has augmented matrix as shown. We solve this augmented matrix, or we solve the system by applying Gauss-Jordan on this augmented matrix. So I'll leave to you to check that these elementary row operations will give this, or will show that our augmented matrix is row equivalent to this matrix. Looking at this matrix, we see that the system must be inconsistent. Okay? Because the rank of the augmented matrix is greater than the rank of the coefficient matrix. So the inconsistency of the system allows us to conclude that it's impossible to express negative 1, 2, 3 as a linear combination of the given three vectors. So the given three vector is not a linear combination of these three. As we saw in the last two illustrations, the problem of expressing a vector in R3 as a linear combination of A vectors is a problem of solving a system of K linear equations in three variables. And this observation actually holds in general. So to see why, suppose in Rn we have K vectors v1, v2 up to vk with components as shown. By definition, a vector in Rn, say with components b1, b2 up to bn, is a linear combination of these guys if and only if we can find real numbers r1, r2 up to rk that make this equation true. And as we've done in the last two examples, the right-hand side can actually be turned into a matrix product by performing scalar multiplications and then adding the vectors and then applying the definition of matrix multiplication. So in other words, this is nothing but a matrix, an equation involving matrices. But on one side, you have a matrix product. So that's what happened there. And notice that in the matrix product, the k by 1 vector is a vector consisting or whose entries are the scalars, r1, r2 up to rk. So in other words, these are values that need to be solved. While in the n by k matrix, the entries are already given. So we'll observe that the first column of this matrix is nothing but the first vector that is given. Second column is the second vector, and so on. The last column is the kth vector. So the problem of determining whether or not b1, b2 up to bn is a linear combination of these k vectors is equivalent to solving the linear system this times this equals this constant, this vector constants. We just need to solve the system and can apply the Gauss-Jordan process to do that. So yeah, the answer is yes, that b1, b2, bn is a linear combination of this if and only if you have a consistent system for this.